This is the concepts video for the next lab, and it's the quantitative determination of sodium ion by ion exchange. Now, this particular lab, we're effectively going to use a water softener. In our natural groundwater, we frequently have magnesium or calcium or sometimes iron, and these substances can actually bind with the soaps that we use to form that scum that isn't removable just by water. You have to use special treatments and a lot of elbow grease to get rid of it. So frequently, we will put that water through an ion exchange column and exchange those magnesium or calcium ions for another positively charged ion, sodium. Okay? Now, that's all very nice and fine, but this time we don't want to exchange magnesium or calcium for sodium. We're actually starting with a sodium solution, and we're going to try to figure out its concentration. Now, one of the problems with sodium is that it's extremely soluble. It's a very strong electrolyte, and it dissolves in water immediately. Plus, the sodium ion only exists in one oxidation state, which is +1. Doesn't exist in any other. It's either sodium metal or sodium plus. Now, these two problems are actually the ways in which we typically identify the concentration of species in water. We change its oxidation state. We did that back with Green George. We precipitate it out, but that doesn't happen with either one of those. Just not going to happen. So it's very difficult to analyze the sodium concentration without using ion exchange chromatography. Okay, now ion exchange resins, that's what they're called, are polymers, and they're organic polymers that have ionizable groups that have been attached to them. Okay, so the resin, which is usually in little bead form, actually has, in our case, sulfite groups attached. Okay, sulfite groups attached. And this sulfite group is going to be the substance that catches the sodium. Okay, now these ion exchange resins, there are thousands upon thousands of them smashed right up against each other, unless you do something wrong, and we'll talk about that in a minute. So it can hold many, many, many sodium ions, which is kind of cool. So what are we going to do with this? Well, we can pour some sodium onto this column and hold on to all the sodium, but what good is that going to do us? We have to have some way of knowing how many sodiums we actually put on, and that's what we're going to be doing this week. So, down here, this is our generic equation. Typically, these sulfite ions are acidified. Okay, they're in the acid form. And they are solid because they're attached to this organic matrix. And then when you send a metal, and in our case it's going to be sodium, like you can see right down here, down, sodium has a higher affinity for that sulfite than does hydrogen. So for every sodium that comes along, it effectively kicks off that hydrogen. The sodium becomes attached to that resin, and it kicks off a hydrogen. Just as simple as that, guys. So now the question is, how do we actually detect how much hydrogen ion or how many moles of hydrogen ion have been kicked off? Well, how do you always determine how much hydrogen you have in a solution, H+? You titrate it with NaOH. So down here I've drawn a little bit better, I hope, to the two steps that you're going to be doing today. First of all, you're going to have your ion exchange column, and specifically this is a cation exchange column. It looks just like a burette. In fact, it is an old burette, and we've packed it with an acidic resin. So here it is all packed nice and tight, and there has to be water everywhere in here. You can't have any air spaces or it'll ruin your analysis. So this has to be completely water, but you'll be talking about that in your video that explains exactly what's going on technically. So there's got to be water in here, and so this is all, these are the solid organic matrices with the sulfides attached, and they're acidified, so they have that H+ on them. Now, what happens is you pour your sodium onto it. And as the sodium comes on, you're going to end up having that sodium replace those hydrogens. Okay, for every sodium that comes onto the column, a hydrogen gets replaced. So I'm just going to do a few of these here, but it's a lot more than a few. So you'll see here that for every sodium that comes onto the column, a hydrogen has been booted off, which eventually will make its way down into the Erlenmeyer flask in which you'll catch the effluent. So you're pouring your sodium ion solution on, and the sodium ions kick off those hydrogens, which eventually make their way down into the Erlenmeyer flask. Now, there's a problem. And the problem is that those darling little hydrogens can get stuck. Okay, they can get stuck. They've been kicked off, but they haven't made their way out of the column. So you have to flush the column with lots and lots of water. And by flushing that column with lots and lots of water, you'll eventually get those hydrogens, that are caught in the spaces in between the little beads. You'll eventually get them to come out into your Erlenmeyer flask. They won't be stuck up here anymore. Okay, so now we have actually exchanged 1 mole, well, 1 particle of sodium for 1 particle of hydrogen. You can see how that worked. And on a large scale basis, it's 1 mole of sodium for 1 mole of hydrogen ions. And we're going to need that kind of stoichiometry, so I'm going to circle it right there. That's going to become important later on. So now what do? Well, we move this flask away. We mark it number 1, and we put number 2 flask underneath it and do the exact same thing again. And then wash it really well to make sure we have all of our hydrogens down in that Erlenmeyer flask. So we have number 2 with its hydrogens. Then we do it a 3rd time, okay? This particular cation exchange column is loaded with enough hydrogen so that we could probably do this 6 or 7 times before running out of hydrogens that can be exchanged. But let's not go that far. 3's plenty. All right, so here we go with our 3 little Erlenmeyer flasks. And we've got number 1. we've got number 1 again. Okay, so we've got our hydrogen in there, and we're going to use a standardized base, okay, standardized NaOH solution to titrate this until our endpoint when we have the same number of moles of hydroxide as we have of hydrogen ion. Now, when I'm done, how am I going to find the number of moles of hydroxide? Same way I always do. The molarity of hydroxide times the number of liters that we got from here of hydroxide will give you the number of moles of hydroxide that you used to neutralize the hydrogen. Now, as always, in our particular case, the number of moles of hydroxide is equal to the number of moles of hydrogen. So as soon as you know your number of moles of hydroxide, you can use this molar ratio to find your number of moles of hydrogen. And as soon as you know the number of moles of hydrogen, you know the number of moles of sodium. So that's essentially what you're doing today. It's not particularly difficult, but you do have to be accurate. You really have to be accurate. This is quantitative, which means we care about how well you do this. Now I'm going to wait till next time to figure out the sodium ion concentration, but I want you to just know a few things first. We're going to be preparing the ion exchange columns. Okay? I'm going to put some water on them so the resin doesn't dry out. The first thing you're going to do, you enter lab and you're going to drain the column until about 1 milliliter of water covers the resin. In other words, we don't want any chance for that resin to dry out. If the resin dries out, then remember I said you had all those beads that had water between them. Okay, they had H2O there. If you let them dry out, all of a sudden, these beads, when they're dry, are much smaller, and you develop cracks, and the water and sodium goes right down through them without doing any exchange at all. So no dry columns, no dry columns, no cracks. Okay, keep these columns wet. Now the first thing you're going to do is add 20 milliliters of water to the column and let it drain until you have 1 milliliter remains, and then you're going to do that 2 more times. Why are we doing that? To get the junk off the column. I mean, we just put this on. Heaven only knows what was left on it when we last put this on, when we last dried this out. Now you're going to do what's called charging the column. You're going to charge the column by adding a fairly strong solution of hydrochloric acid. And at this point, the H pluses will attach to all those sulfites that are in there. Boom, all of them. Okay, so we're going to drain the acid off slowly so it gives it a chance to interact with the resin. And then we're going to do it 2 more times. We really want to make sure every single one of those little resin beads has H pluses on it. This is called regenerating the column or charging, like I just said, and this guarantees that all those little sites that are on the resin have H pluses on them. They're in the acidic form. Now we need to rinse this, and the reason we need to rinse this with more water is because not only do you have H plus sticking on those sites, you have H plus all in all those little channels and crevices around the beads, and you don't want that. You want only hydrogen ions on the beads, okay? You only want the hydrogen ions that are attached to the beads, because those are the only ones that are going to give you the 1-to-1 ratio. If you have, and I'm going to put the extra hydrogens in a different color, if you have some extra hydrogens just floating around here that haven't been attached to anything, when you put your sodium on, some of the sodium will exchange like it's supposed to, but the water that the sodium's in will push off extra hydrogens. Okay, the water will push off the hydrogens it's supposed to, but it'll also push off some of those extra hydrogens that were just floating around. So our relationship, 1 sodium to 1 hydrogen ion, will not be true. It's ruined. Your whole experiment's ruined. So you have to wash that column. After you acidify it, after you charge it, you have to wash it to make sure that there's none of these extra hydrogen ions hanging out in the pores of your resin. And Mr. Proetta will show you exactly how to do that. Now, we have another problem. Our column is good. We are ready to go. But we have sodium chloride solution that is too concentrated. It's too concentrated. So you have to make a dilution. Okay, and you're going to have a 25 milliliter volumetric pipette, and you're going to take 25 milliliters out of your sample of NaCl and put it into a 250 milliliter volumetric flask. Okay, so let's see if we can figure this out. 25 milliliters, that's our original volume, V1, times your M1, which you don't know, okay, is going to equal M2 V2. Now, your M2 you're going to figure out in the experiment, and we'll talk about that next week. Your V2, however, is 250 milliliters. So in other words, you're going to dilute your original sample by 10-fold. Okay, if we're just solving for M1, we divide both sides by 225, and you can see you have a 10-fold change in concentration. Now, at this point, I'm going to turn this over to Mr. Proetta because things do get, well, it's very precise. What we want you to do is very precise. So I've shown you now how to charge that column, and I've talked to you about the fact that you're going to have to dilute your original solution of sodium chloride, or it's going to be too concentrated and wipe out your column. And now Mr. Proetta is going to take over and show you how to do the actual experiment.